Okay, let's continue on with our discussion about semiconductor fundamentals. Were there any questions so far? Material? Okay. So I was looking over the homework statistics. I think a lot of students did very well on it. I was very surprised. It was kind of like a test in there, not a test of your knowledge, but a test of your kind of skills, like learning skills. So what did you think about that question? The first one, where it asks you to calculate the carrier density. Yeah, that's very valid. So I will go over the problem on Wednesday, but what I wanted to kind of illustrate, well, let me first say the homework was due yesterday or today? Tuesday. Okay. So I'm going to go over the problem on Wednesday. So I'll extend the homework until then, and you have unlimited attempts to get it done, right? So the point was that as an engineer, how would you tackle a new topic that comes up, right? So basically, you are right now, I would say, what, mostly juniors in the class, right? Sophomores, okay. Almost half of your education is over, right? You're at the end of your second year, moving on to the third year next, and 2 more years. So 50% of your education is done. Within 2 more years, you'll be working independently by yourself as engineers. And you'll spend the rest of your life as an engineer, 20, 30, 40 years. So you'll be working somewhere for any corporation, academia, doesn't matter where. New topics keep coming up every single day. Are you going to go back to school and spend a year in college every single time? No, right? I mean, there's so many new things have come up since I graduated. So the point is, as an engineer, you are expected to tackle new things every day. Okay, you are not expected to just keep doing the same things every day. You're expected to tackle new. And when it comes to new, you have to learn how to learn. Okay, so you have to learn. You have to teach yourself how to learn. Okay, so this small exercise was about, okay, you have limited amount of information. What else? What other resources can I access and learn to solve that problem? Okay, so just think, there's no penalty on the points. This is just as a self-reflection of their own learning ability for every single student, all right? So again, as I said, I will go over the material. We'll go over some material today, and then I'll go over some material on Wednesday, and then I'll tackle and explain how we, apply the equations for that problem, all right? So there's no trick or anything in there, again, because I'm not trying to penalize students or penalty. It's just part of a little bit of learning experience that you can do a self-assessment. All right, so you stop here at this equation. This equation basically describes how we can calculate the number of intrinsic carriers that are generated at any given temperature, right? So we focus on these charts here. It shows you the temperature dependence, right? Temperature on the x-axis and the carriers that are generated on the y-axis. And you can see this would be 270 here, approximately. Oh. That's basically zero, right? 273 degrees. 273 degrees is 0 degrees Celsius. So below that, you can see the number of carriers going up from 0 to up to 10. Seems like a large number, but it's really not. It's not sufficient for conduction, okay? Not sufficient for conduction. And that's, of course, what makes it a semiconductor. As the temperature keeps rising from above 0, you have more and more covalent bonds being broken, more intrinsic carriers being generated, holes and electrons present in an equal number, right? At the same time, when an electron breaks its bond and leaves its spot, hole is created. It might move around somewhere in the lattice structure. And while it is moving around, it could find another empty spot and jump into that spot. When it jumps into an empty spot, that electron is said to have recombined with the hole, and a negative and a positive charge disappears. Okay, you all with me so far? Right, as the temperature increases, electron acquires enough energy to break free from its bond. When an electron leaves, it leaves behind an empty spot in its place, that is a hole. So an electron, for every free electron that is created, there is a positively charged hole that appears in the silicon structure, in the semiconductor structure. Now, it's going to wander around randomly, but eventually it's going to end up recombining, falling into an empty spot somewhere else in the lattice structure. When it falls into an empty spot, it is said to have recombined, right? It's said to have recombined, and that takes out that negative charge and the positive charge. The amount of time the electron is freely available to move around is known as the carrier lifetime. It's known as the lifetime of that carrier. Okay, they are known as carriers because they are carrying charge, and the amount of time that it spends outside of a spot is known as the carrier lifetime. Okay, carrier lifetime. So the time spent outside of a bond. So if you look at the temperature dependence, it rises all the way to 10, 11, 12, and then you might see a slight linear shape right around here. Okay, and we'll take a closer look at it in the next few slides too. So again, temperature increases, more and more thermal energy is imparted, and more thermal energy is imparted, more and more electrons are available for conduction. So the effects that they have are very important because of the amount of applications that we need, right? If you are using your phone in this area, room temperature, it's going to work fine. Laptops, phones, any electronic device, because these are consumer electronic devices. Okay, so within a specific temperature range, the electron hole generation is controlled, right? Because of the thermal energy. If you take the same electronic device to Antarctica, it's going to freeze up. It's not going to work. Why? Because the design of the circuit, the design of the device does not compensate for the loss in the intrinsic carriers. Okay, so the devices are created and designed in a way to function at different temperatures. Everything that we study in this course is specifically just for consumer grade electronics. We are not looking at industrial grade. We are not looking at military grade. Okay, you've often heard times this is military grade equipment, right? Because military grade equipment needs to operate in extreme environments, from the extreme cold to the extreme heat. Industrial applications, let's say underwater electronics comes to mind. You have underwater cameras that go deep sea diving, high pressure and very, very low temperatures at the bottom of the ocean, even closer to the surface. And so electronics need to be able to function in those kind of environments. That's where the industrial applications come into the picture. Military applications, again, kind of similar to industrial, but even more extreme. Submarines go far deeper than any other craft that we can go through. There's outer space. We send electronics to outer space. We need electronics to function in that kind of environment. Yes. So it depends on, well, it affects more like fabrication. So the question being asked is, how does pressure affect it? Well, pressure would just destroy it if, like anything. So obviously, if you're using electronics, then it will be sealed inside inside a protective cover. So that would, like submarines, humans cannot survive at the depth that submarines can survive. Yet, it's the submarine is, yeah, airplanes, submarines, they're all pressurized for human comfort. Because we are not sending the electronics out, out by itself. Yeah. I mean, if you took just a phone and just trying to use it underwater like that, it's going to get destroyed. But if your phone is placed inside a protective cover that can withstand that pressure, that's fine. So yeah, pressure not so much, but temperature, yes. Temperature, yes. Okay, so the intrinsic carrier concentrations, typically 10⁻⁹, 10⁻�10, seems like a huge number, right? 10⁻⁹ is giga, trillions. So it seems like a huge number, but it's very misleading. The way the units are written, it's basically numbers of carriers per volume of 1 cubic centimeter. Okay, it's not in microns, it's in centimeters. So 1 cubic centimeter, if you convert to microns, each centimeter is about 10 millimeters, and each millimeter is 1,000 microns, 10⁻⁷. No, 10⁻⁵, right? And 1 cubic volume, so 3 times. So if you go down to the micron, it just turns out around 4 or 5 electrons per cubic micron, right? Which is right here, approximately. Okay, approximately. So again, intrinsic carrier concentrations, I think when they first started this, it became, they use centimeters, and it just became the de facto standard. So we still use it to this day. Anytime we send our dosing requirements for ion implantation for any kind of processes, it's always per centimeter. So the units here are basically the numbers of carriers that are generated per volume of cubic centimeters. And later on, we'll see it will be number of atoms per cubic centimeter. Again, anytime you are working with these equations, please pay attention to the units and the unit prefixes. Because if you just take this number as it is, your answers will be incorrect. Okay. All right. So, needless to say, I mean, I think every professor, every researcher that I've had conversations with has always had not good things to say about like centimeters, or why we are using centimeter cube when we are dealing with like electrons on a large scale. Okay. So it seems like a large number, but it's not sufficient for conduction. Okay, we can't do anything to it. Okay, we can't make resistors out of it. We cannot create conductors out of it. And the reason, simple reason, is we cannot control it. So in order to control it and to create a conductor, what we need to do is we need to introduce more free electrons, right? More number of electrons that are available for conduction, the closer it is to becoming a conductor. So what we do is we introduce external material into our semiconductor material. Okay. That external material is an impurity. In this case, the impurity simply refers to something that is not inherent in the material itself. Okay. As an example, if our material is silicon, then anything that is not silicon and is introduced into our semiconductor material is an impurity. And that is where the magic of semiconductors happens. Okay. By introducing impurities in there, we control the number and the amount of impurities that we are introducing. Hence, we can control the types of devices we can build. Okay. Again, intrinsic semiconductors by themselves are not very useful. Again, they are semiconductors. We cannot use them as insulators. We cannot use them as conductors. But if we introduce external impurities in there, we can now control how our device functions. So then the next question is, what kind of impurities do we introduce? Well, these impurities are specifically from column 3 and column 5 of the periodic table. Column 3 elements have 3 electrons in their outermost orbit, and column 5 elements have 5 electrons in their outermost orbit. So if we introduce an element from column 5, 4 of those 5 electrons will bond with 4 silicon atoms. And that is being illustrated here. You have a column 5 compound or element right there that's introduced into the silicon lattice. It has 5 electrons marked by this 5. And this is the one extra electron that is now freely moving around inside our semiconductor material. Does that make sense? Let's take a pause, think over that, and let me know if you have any questions. Any questions? Okay. So if you introduce column 5 element, you have 5 electrons. 4 of those 5 electrons will bond with 4 neighboring silicon atoms. And the 5th one is left free to move around. So now we have introduced extra electrons in our semiconductor device. And all of these extra electrons, meaning 1 electron for every single atom that we added in there, is now available for conduction. Okay. And we can control how many atoms we are introducing into the silicon surface. Well, not down to the single atom, but we can control an approximate number. Okay. There are specific processes we use to actually do this introduction. All right. So if there is an extra electron that has left its home atom, that home atom now has an extra positive charge. Right? You have a column 5 element that is introduced into the lattice structure. 4 of the electrons will bond with the 4 neighboring silicon atoms. 1 extra electron is free to move around. So you have 1 extra negative charge that is moving around. But because that electron left its native atom, that atom now has an extra positive charge that is bound with the nucleus. Right? So the important or the key point is that overall, the overall charge is neutral. The overall charge is neutral. Even though there are extra electrons available for conduction, the overall charge in that semiconductor material is completely neutral. So 1 extra electron from column 5 and that negative charge is balanced with positive charge in the nucleus. So overall charge is neutral, or the sample is neutral. And since there are a lot of extra negative charges available for conduction, this is known as an N-type material. It's an N-type material. And because the impurity atom is donating an electron, that atom is known as a donor atom. It's lost an electron, so it's now ionized. That ionized donor atom has a positive charge. net positive charge. That positive charge is fixed in the lattice structure, whereas the negative charges are free to move around. So now when we apply an electric field, those free to move around electrons are available to conduct. Okay. Same thing happens when you introduce a column 3 element. When you introduce a column 3 element, it'll bond with 3 silicon atoms and needs a 4th one. So it's going to pull an electron from an existing silicon atom, which creates a hole in the other silicon atom. Okay. So let's say there are 5 silicon atoms. You introduce a column 3 element between those 5 atoms. It's going to pull an electron, or not pull. It's going to share one of its 3 electrons with 3 of the neighboring silicon atoms, and it's going to pull a 4th from the 4th atom. So now it has a stable structure, but it's now created a positive charge somewhere else. So this is column 3 element. And this is the missing or hole, right? This is the one that's missing. So it's hole. So it creates a hole somewhere else in the lattice structure. And then from that hole, the electrons and some other electrons can jump into those. And so an excess of positive charges are now created in that structure. Same principle, instead of negative, now you have extra positive charges. Okay, because when an electron leaves, it leaves behind a hole. That hole is associated with the nucleus. The nucleus is an extra positive charge. So in summation, if you introduce column 5 elements, you have an extra electron, you have negative charges. So it's an N-type material. When you introduce column 3 elements, holes are generated. And extra positive charges are created. Hence, a P-type material. Okay, it's a P-type material. Yes. Yes, we're gonna look at that in next few slides. So if it's donor for electrons, so the question being asked, if it's a donor, why is it positive? So the keyword donor, what is it donating? It's donating an electron. So if it donates an electron, the electron is gone, right? So there are 5 electrons, 4 are orbiting, 1 leaves. But for every single one of those 5 electrons, there are 5 positive charges in the nucleus. So if 1 electron leaves, the positive charge still stays with that ionized atom. And hence, a donor atom is ionized, and it is said to have positive charge. This atom that we introduced here, column 3, is going to accept an electron. Hence, it is known as an acceptor atom. And because it's an acceptor atom, again, there are 3 electrons balanced by 3 positive charges in the nucleus, but it acquired a 4th negative electron. And because it's an extra negative charge, it's now an ionized acceptor atom with a negative charge. Okay, let's take a pause while you think over that. Yes. So column 5 is typically boron. And sorry, donors are phosphorus and arsenic, and column 3 is boron. Boron creates a P-type, and then phosphorus and arsenic create N-type. In the clean room here, when we create our diodes, we use phosphorus and boron. So these are the most common donors, as I said, in the clean room class here. We use phosphorus and boron to create our P and N type materials and then create diodes from there. Okay. Now, remember I said intrinsic material by itself, intrinsic semiconductor by itself is not very useful. So we introduce external impurities in there. And the amount of impurities that we introduce is controlled. Okay. We of course cannot control it down to the single most atom, but it's controlled to a certain extent. Yes. So the question being asked is, does the amount of doping affect the current? The amount of doping, right? And absolutely, the answer is yes. So the amount of doping is what allows us to create a variety of different devices. So there's a physical geometry, obviously, of the device. Plus, the most important thing is the amount of doping. And there's another slide next, which tells us how much doping is sufficient, right? How much doping is sufficient. So before I say that, the inclusion or the addition of impurity material into our semiconductor material is known as doping. And the semiconductor is known as a doped semiconductor or doped material. Doped semiconductor. Okay. And then when we typically, if we perform a process called ion implantation, we refer to something known as dosage. Dosage is basically how many atoms per, excuse me, how many atoms we like to implant per square area. Okay. The process that we use here and in most academic clean rooms is known as diffusion. We take our liquid material that contains our boron or phosphorus. Maybe we take our sample wafer, put it on a wafer chuck, deposit the liquid on there and spin it at about 4,000 RPM. It creates a very nice thin layer. And then we stick it in a furnace at 1,000 degrees C. It's like baking cookies or spreading butter on bread. You spread butter on bread, stick it in a toaster oven, butter is going to sink in. So you have your silicon wafer, you're going to spin or coat it with your boron or phosphorus material, and you stick it in a furnace. The only difference between that and oven is the temperature. 1,000 degrees C, it's going to sink in within an hour or two. And so now you've introduced external impurities into your semiconductor material. Doping process of two kinds, ion implantation and diffusion. Ion implantation is a very specific and very, very expensive process. So there are companies who just do specifically ion implantation. There are businesses throughout this state. When I was in grad school in Louisville, Kentucky, we used to send our wafers out here to California to a business. They would do ion implantation for us. All right. So let's go to. All right. So intrinsic semiconductors are the ones where the carriers are generated solely due to thermal energy, right? Thermal energy is applied. Electrons acquire sufficient energy to break their bonds and are freely available. It's inherent. It's inherent, hence it is known as intrinsic. So intrinsic semiconductors. When we add external impurities into our intrinsic material, it's now external. And so these are known as extrinsic semiconductors. So a doped semiconductor is known as an extrinsic semiconductor because we're now introducing external impurity dopants in there. Now, obviously, the goal is that we want to control this device, right? We want that device to function according to our specifications and according to our application. So we want to control how many impurities we implant in there. This is a graph here where it shows us both the intrinsic and the extrinsic ranges. So here, you see the one in the green, and I'm going to talk about these notations just a little bit. The N basically, and here's where it gets a little confusing. The N in this case simply stands for number of carriers. That carrier could be an electron, it could be a hole. Okay, but that lowercase n is also used to indicate electrons. And then lowercase p is used to indicate holes. So it gets a little confusing. Anyway, let me talk about this chart and then I'll talk about the notations. So here in green is basically where you have intrinsic charge carriers that are generated due to thermal energy. And it's basically the number is actually low, right? Intrinsic is around 10⁻⁹ or 10⁻⁴ or lower than that. Then extrinsic range is around 10⁻�XVI, 10⁻17, 10⁻18, even all the way up to 10⁻20, right? So all the way up to here, I would say about 500 or 550. 550 Kelvin. The extrinsic, meaning the externally implanted impurity, is the dominant charge carriers. But at higher temperatures, there is enough thermal energy to break multiple bonds, and there's a rush of charge carriers that are now available. So at very higher temperatures, intrinsic charge carriers contribute more rather than the extrinsic material. Okay, because the extrinsic is controlled, right? Once we create a material, we have introduced, let's say, 10⁻�XVI electrons or holes in there. But with increase in temperature, intrinsic bonds or more intrinsic carriers can be generated. But extrinsic carriers are going to remain exactly the same. They should not change because that's basically we introduced in a process and they would not change. Okay, so at higher temperatures, the carriers are dominated by the intrinsic carriers. Okay, then let's talk about notations. Ni, N in this case represents electrons and holes. Okay, it's a generic representation for electrons and holes. The I stands for intrinsic. And then again, if N is used as a subscript, that indicates electrons. And if P is used as a subscript, then it indicates holes. So it gets very confusing. All right, so we have NN and we have NP. So let's write that down. Number of holes. In the next slide, you will see that instead of using just NP, which is confusing, we use PP. Notation P with a subscript of P. Okay. All right. So then we have ND, which is number of donor atoms. and Na is number of acceptor atoms. All right, 2 o'clock out of time. All right. I'll pick up here. So we'll end class here today and we'll pick up here on Wednesday. All right. If you have any questions, we have a few minutes before my next class.